Hello. As Frank said, today we are going to focus on, we have three talks focused on regional implementations of ocean models with MOM6. And the way this is loosely structured is I'm going to start with an overview of kind of what got us here and our design philosophy for the essentially open boundary conditions that have been implemented in the MOM6 code. And then Kate is going to follow that with a more step-by-step practical in case you wanted to run right after our talks and set up your own regional configuration with MOM6, what you might need to think about and do. And then Bob Helber later on, who has been independently working with this code in some applications in Nordic seas, he will dive a little bit more deeply into the applications. My talk is going to be half and half, a little bit on what the boundary conditions are as they are right now, and then some early applications of these configurations. What you're looking here are some, in the title slide, are two of the early configurations that we ported over from ROMs, which we've had decades of experience with. So that seemed like good targets for us to get going in terms of configuring MOM6 regional. This is a slide here that is changing by the day in an exciting way. This whole project started, I guess it's about 3 or 4 years ago now, where we were looking to have a regional model that might have the same dynamics and numerics that some of the global models have as the global models are moving towards higher and higher resolutions. They're beginning to think in terms of some of the physics that might be interesting to higher resolution regional models. And in the same breath, there's a lot of experience in the regional modeling, ocean modeling community at high resolutions and coastal processes that could be of benefit to the global models. And it seemed like it was time to really, and the models have matured enough that it seemed like it was time for us to try to work with one code base that can handle both the global and the regional models. So naturally at the time, we got together with the folks at GFDL, and they've been obviously involved with us in the development of regional MOM6 from the get-go. And then, of course, Kate Hedstrom at University of Alaska Fairbanks has been significantly involved. And there's other people here at NCAR as well as they're beginning to pick up. So there's a beachhead form there for regional applications, especially with MOM6 now. And there's others. And I'm forgetting people. There are people that are not named here, but there's other people that are slowly beginning to pick this work up, including people at other NOAA labs in Israel, PMEL, and AOML, and others, and the Navy as well. So there's a burgeoning community for these applications and interest in this work. So I'm not going to go into the design of MOM6. Bob Holberg did that, I think, in the first of the series here, and there was a nice and comprehensive talk about all the equations and numerics that go. So I'm just going to kind of informally describe what we were trying to achieve with the implementation of open boundary conditions in MOM6, and then I'm going to jump to some of our early applications, showing you where we are, what the strengths are, and what we still have to work on. So based on some of our past experience where we tried to merge ROMs with POP and thinking in terms of nested climate and some of the experience that the atmospheric people have in terms of nesting, we wanted to have a fairly general definition of what a boundary condition is or what an open boundary condition can be. And with that in mind, the open boundary conditions in MOM6 conceptually were designed to be thought of as segments that can either be on the edge of the domain, so there could be like a natural boundary, that's where you're running out of your regional model, or you could think of them also as an internal segment, which is an internal boundary which is formed out of various segments that is basically a line of points where you may be solving a different set of equations, in this case, radiation equations that will mimic what an open boundary condition is. So here you see it. And the idea here again is looking towards a future where we might want to implement a two-way nested domain or have two adjoining domains. And as I'm looking at this, I'm thinking maybe this would be an interesting way to also, for example, do things like narrow straits in a global model, or anywhere else that you might want to, for whatever reason, do something slightly different than the normal equations that you're solving. So, so that's how these things were conceived. And if you look a little bit more practically at what that means, you have your domain that's your inside, right? And you have some information that's sitting outside. And here you have, for example, an internal boundary segment or series of segments, an internal boundary sort of boundary line that's formed out of 4 segments. And to get information to the inside, you don't necessarily rely, or you don't rely on any information that sits outside of your boundary. So it's all internal to whatever information you have. On the Arakawa grid, which is what MOM6 is, the information that you need to pass across a boundary is the free surface, the normal velocity, and the tangential velocity, which was something new to us coming from the ROMS world. That is due to what I think Bob described in his first talk, the vector invariant formulation that comes in. So you, and I'll mention that again a little bit later. There's the need to pass the tangential velocity across the boundary as well. And of course you have tracers, temperature, salinity, at the very least, and of course all the biogeochemistry that you may be interested in running. And there's a possibility, well, there's also the need to specify something for the layer thickness, but that's turns out to be a slightly more complicated question beyond a very simple implementation of that because of the AL vertical coordinate. So the boundary conditions are such for the barotropic mode. We are using Flather, the Flather condition, which requires the specification of the barotropic and the free surface outside of or on the edge of your domain. So we call these external values. And this has worked really well for us in ROMS, and it's working very well in SMOM6 equivalent as well. The problem really starts once you go to the baroclinic. So all the headaches that we get from the open boundary conditions, and there are plenty, they come from this. The original conditions are based on Orlansky, so radiation conditions, which have been modified, which will only specify the normal phase velocity. So you do a radiation condition based on the normal phase velocity at locally at the boundary. And it's been modified in the 80s, I think it was 84. So the paper by Raymond and Kuo that allows you to consider both the, well, that paper I think was 3D. You can do the two-dimensional radiation or oblique condition for the phase speed, and based on those you can compute the local normal phase speed at the boundary. And here in this equation, the phi are the phase speeds at both x and y, if you will, directions, and again they're a function of local information. This is for the outgoing, and on the inflow, you can set it to either 0 gradient, or you can nudge these things, as has been done in ROMS, to some external value, and then you can set what these nudging coefficients are. So if you have information that you really trust and you want the interior of your model to really move towards that particular value quickly, you can set a very short time scale. But if you have waves that are, for example, leaving your domain, you can set it on a year or 300 days or whatever makes sense for that particular application. Basically, it gives you two tunable knobs that you can use to try to work the boundary conditions to look as best as they can for each particular implementation. There really is no canonical value that you can use for this. For those of you here that are not thinking about open boundary conditions on a daily basis, the open boundary condition problem is difficult because it's a mathematically ill-defined problem. For the barotropic mode, which is closer to a hyperbolic system, the phase speeds and the characteristics are known, and not so for our baroclinic velocities. So we end up at the end of the day trying to overspecify the problem to constrain it to look reasonable. So a lot of the intuition of that you have about a particular domain or flow and the way it should look like comes into implementing any particular domain that you have. As I mentioned before, in MOM6 we have the need to bring in the tangential velocity as well, and that's needed in the strain and vorticity. For computational strain and vorticity, again, vorticity is used in the Coriolis term, which arises from the vector invariant formulation that MOM6 uses. It can be set to a zero gradient, so a free slip, or you can specify values for the gradient of the velocity, or you can compute them from the radiation condition. Or you can always specify zero strain as well. Tracers, this is still an emerging development. There are prototypes for this now. There's been a lot of work done in the last few weeks, and this is coming online hopefully in short order. The way they've been designed is to have a reservoir that has memory of the fluid that left the domain, and then as information comes in, you can then mix it, and you can set up mixing lengths relative to the contribution of each tracer on the inflow. And as I alluded to before, the layer thickness that's used in both continuity and the Coriolis computation right now, it's set to no gradient, and to do other options with that may be complicated because of the AL vertical coordinate. So this is something that down the line we may want to revisit if that's the one thing that's going to make the solution that much better. So if you look at the code, and Kate will talk about this a lot more in her talk, is you can basically set it to be simple conditions. So you clamp it to some value or gradient or the flather for the barotropic mode, and we have Orlansky and oblique for the radiation, and then you can nudge these things to the baroclinic modes to with particular timescales to either ease or impose boundary conditions at different timescales. So the first thing that was done for the development, there's I think 2 or 3 different, at least, test cases that we would recommend for people to start looking at if they want to play with these things. The first one was this thing called the dumbbell. You can see the shape of it in the top, and that's your full domain. And the middle and bottom layers here are 2 different boundary conditions. So basically we cut it out. It's exactly the same grid, except that now instead of having the full domain, you will extract boundary conditions from where you have those vertical blue lines and impose them at the at the boundaries. And you see, of course, that at high enough resolution, the models start diverging from each other because of the implementation of the boundary condition. And there's a few other test cases out there for people to play with, and if you want to actually play with boundary condition itself, you can try to test it on those things. So I'm going to move now on in the next 10 or so minutes to different implementations that we have. The one that's most advanced for us is the one in the Northwest Atlantic. This is a model that we've developed, I guess 2013 was published, and it's relatively cheap to run for several decades, but it's big enough that it gives us some sense of how the model is doing, and we have a lot of experience with this in running it with ROMs and many papers that came out of this already. And we are seeing, if you look at the bottom, right now it's being run with 3 different vertical coordinates. One of them is with a Z-star with 50 vertical layers. One is the Z-star with 75, so higher resolution in the vertical. And one is with a HICOM-1, which is a coordinate system that MOM6 has adapted or borrowed from HICOM implementations, where it's an isopycnal interior transitioning to a Z-star coordinate on the shelf. And here's your eye candy for today. This is basically, you're looking at normalized vorticity here. And again, this is what you're saying is that we are now able to run MOM6 as a regional configuration and are beginning to look at features that look to, at least to the eye, as recognizable or for this particular part of the world. If you tune your eyes closely to, I don't know if you can see my mouse or not, to the boundaries, you will see that though they're not perfect, and here you can see some ringing reflections from it, they are working reasonably well, at least compared to what we are typically used to. And we have run this now in various configurations for about a decade each. Here is looking at the Gulf Stream path. This is work that Duzhuan Kang in my lab at Rutgers is carrying out. So 2 different ways of looking at the Gulf Stream path, which is the dots here. So the dots are the observation, and then we look at the 2 different vertical coordinates. So one degree of freedom that we have with MOM6 that we never did with ROMs is the ability to have different, not only a mixed vertical coordinate system, but just different coordinate systems, period, right? So this is what it looks like right now. We are beginning to try to quantify what the difference is. We have to develop yet an intuition as to what, or any particular domain or region, what would be a good vertical coordinate implementation. And we really don't have a sense a priori of what that might be. I mean, I could justify to myself why I may want a pure isopycnal or a sigma or a Z, but in reality, I think this is going to be very much domain and configuration dependent. And so we need to start figuring out how we are actually going to quantify these things. So in this case, we are looking at the total mean and eddy kinetic energies. Here's comparing the two vertical coordinate systems with the same number of vertical layers, so 75. And you see that there are significant differences, right? So just taking the code and running it with this hybrid isopycnal /Z, which is the HICOM-1 coordinate system, or running it with simply Z star. If you look, for example, just south of and offshore of the separation point at Hatteras, you see that there's a much stronger recirculation in the HICOM case that's generating a lot of local energy, which in theory is being absorbed from somewhere else in the code. So this is just, again, us building experience with this model and highlighting to everybody in the community the kinds of questions that we are going to be exploring, and everybody should be exploring, in the near future. Looking at transects, here's again one of Hatteras, you can see that even the structure in the vertical, in the interior of the ocean can be quite different between the two vertical coordinate systems. More of that. Okay, I've asked people that have been involved early on in these implementations to please provide me with some input on what they're doing with regional MOM6. So Alan Walcroft and Eric Chassinier at Florida State, they are moving to implementing their Navy global ocean prediction system to MOM6. Though I believe it's still going to be called HICOM. I don't know, Alan, which I think is on the call, can clarify that for people that are interested. And they are starting with a global 112 degree, and they are right now running it with a repeat atmospheric forcing for 10 model years. And then they are taking this and then extracting a North Atlantic 112. So it's the same. So it's just a subset of the global grid that I believe that they are running. And in this particular case, with relatively simple, so sponge, open boundary conditions. And again, this is allowing them to really test in more effectively or more efficiently numerical developments that they ultimately may bring back to the global model, and then they have further downscale that, if you will, or subsample this to a Gulf of Mexico domain that you're looking at here, and these are actually running with the full radiation. This particular domain is now running with the full radiation conditions as they exist now in MOM6. This is an implementation. I have a few more minutes here. This is an implementation from Kate Hedstrom, who will be giving the next call. And the main thing here is to show that this is now being run coupled with a sea ice model. The figure on the left is ice thickness after some time of simulation. And this is not the great solution, but what was happening was that the sea ice was not able to leave the domain down by Greenland, so it was accumulating. And I believe that since then, work between Kate and Bob Holberg, they've designed a boundary condition that allows the sea ice to advect out of the domain, and this is looking much better now than this figure shows. But this is just, again, highlighting a configuration. The figure on the right is an initial ice concentration that was recently implemented so that you can start a regional simulation now, I guess the global as well, probably, with a specified ice from, in this case, from reanalysis, Glorious, I believe. And you don't have to start from zero and go through several years of integration to start forming ice as needed. Okay, this is, I have, I think, 2 more slides here. This is a MOM6 implementation in the California Current. This is one of our old ROMS domains that Liz Drenkart, who is now at GFDL, used to work in my lab. Again, another regional area that we've had decades of experience in trying to configure and run this domain. And I'm putting it here because it shows you some of the difficulties that you see with the open boundary conditions. You start seeing this, again, you're looking at vorticity here. You start seeing these rim currents, especially on the western boundary. So we've always, this has always been a challenge, a challenging domain for us. Somehow in the Northwest Atlantic model, where this advective flows dominate the solution, we seem to do better than here, where you have these Rossby waves trying to go out, and they're not quite seeing, they are seeing a wall, they're not quite seeing nothing there. And these reflections then, I guess through local dissipation and other processes, start forming these currents that, or this divergence at the boundary, which then drives along boundary flows, and you see some example of that. I would add that this looks no worse, or yeah, no worse than any solution that we ever did with ROMs with this kind of configuration. So it's a good target for us to try to both understand how MOM6 is working, but also on how to improve it. And the way that we, so I'm going to move on to, this is a slide I just got about 10 minutes ago from Scott Bachman. And the reason I'm going to put it here for a couple of reasons. First is to show another regional configuration. This is in the Eastern Tropical Pacific. This is a recent, it's a project that was recently internally funded at NCAR. That is has some novelties to it as well. It's going to, but being an eastern boundary condition, the first thing that an eastern boundary type domain, one of the first calls I got from Scott was about the rim currents that I just showed you in the California current before, and the way we typically control those in ROMs for very long integrations was to add nudging or sponge layers near the boundaries, and I think he's taken ownership of trying to do that for MOM6 as well. And other novelties of what this particular domain will do is to add surface wave forcing, as well as Lagrangian particle releases, and very interestingly also a very high resolution, order kilometer or two, I believe, atmospheric forcing with MPAS. So not only are we going to have a high resolution ocean here, but also very high resolution atmospheric forcing. And again, this is one of the nice features of having this regional model, is the ability to test all kinds of configurations and couplings like that that would be much harder to do in a global sense. So that's really all I wanted to show for today. You know, the summary here is that this community is rapidly building, and the applications that are being used are from weather to climate. We just got funded recently to contribute a high resolution ocean model for UFS. So from the Weather Service, and of course we have our long-term interest in climate and downscale climate for coastal applications, for fisheries and ecosystem work as well. You have the sense that this is a hot air balloon that's kind of taking off, and we're still trying to load it with some features. I would say that we're not quite at version 1 yet, but we are very, very close. And some of the imminent development that's going to get us there quickly is the inclusion of explicit tides. There's already Andrew Ross, who's a young postdoc at GFDL, has taken that on, and there's also already prototype for some of the tidal components. So we expect that within the next 3 to 4 weeks, there will be a full implementation of explicit tides in the regional MOM6 so that we can force it through the boundaries. Tracer and biogeochemistry boundary conditions are being worked on by Niki Zadeh, also at GFDL. He just started on this in the last couple of weeks. There are some conversations going on right now as to what would make the most sense for a variety of tracer boundary conditions with different requirements, and then the inclusion or the implementation of these sponge layers that Scott Bachman is and I believe others at NCAR, maybe Gustavo and Alper are working on. Our long-term wish list remains from decades or years of working with regional models is to have a robust two-way nesting capability so that we can run global and regional models synchronously in a downscale situation, and looking not only at the impact that the large-scale climate may have on regional domains, but also what impact will resolving some of these coastal features may have on large-scale climate. And it would be, and I believe that there's moves in this within NCAR in particular to fully embed a regional ocean model in the global coupled model, so then we can take advantage of all the development ultimately that's being done for both global models, the dynamical cores, but also physics and parameterizations and coupled models that is going on in the various labs. And finally, is it time now to think about improving the actual dynamics of boundary conditions beyond this Raymond Quo or landscape type conditions? And there's some ideas that we've been floating around. And this is perhaps a much longer term wish, but I'm hopeful that that we haven't seen the best open boundary condition implementations out there yet. So I'll end with that. I'm happy to answer any questions that people may have.
Okay. I think Steve Griffiths is up first. Go ahead, Steve.
Yeah, I was hoping you'd read it, Frank. But all right, so a detailed question on the Bear Clinic OBC slide where you were talking about Orlansky. You used the symbol phi. Is that in the model? Does that correspond to U and V, the horizontal velocity, or something else?
No. Phi is a local phase speed computed from the gradients of velocity and other things. Yeah.
So what do you do with that?
What do you mean? So you compute so the phase speed will tell you whether you have information that's going out or coming in, right?
Okay.
And then based on that, then you can either radiate your velocity out or take a value from, let's say, a boundary condition file that you may have or from an external model.
Okay, so it gives you causality or characteristics. Okay. How readily extensible is the OBC code to two-way nesting? And do you think you need something like OGRIF, or would your vision be something independent of something, an external package?
I would like to see it independent of AGRIF. I mean, AGRIF had some. Okay, I should start by saying I've only read about it, reviewed some papers on it, but I haven't actually run it myself. But I think the AGRIF code had some constraints to the way you could implement this, right? So you had to have collocated grids, and I think it limits. When I was looking at it, years ago, it was only you had to kind of convert your code to Fortran 77. I think that they've gotten beyond that. I think it would not be wise to necessarily go to a package like that that may or not have sustained support in the future. And I'm not exactly convinced that it's even necessary to do that. I think the two-way nesting will require some thought, but I think what we have done right now is within the MOM6 code is designed that the data structure that holds the boundary condition code to deal with it, whichever way we ultimately end up implementing it. So I don't think that we're quite ready for that, but and there's probably a much broader conversation that needs to happen as to what would make sense to do it. But I would not necessarily go down the path of AGRIF from what I read about it.
Okay, great, thanks.
Other questions for Enrique?
Enrique, it's Tony Rosati.
Hey, Tony.
Just curious how you envision going forward, not just on the ocean side, but on the atmospheric side, especially are you thinking of a grid that's the same as the ocean grid in terms of resolution? I mean, I'm just thinking about how you would use this in predictions.
Well, so are you talking about sort of weather scale, or are we talking about climate scale?
I'm asking you, what's your vision?
Well, so the first thing I think that we need to do is stick this in the coupled model, right? So we need the
right.
We need the coupler to negotiate the atmosphere-ocean coupling, right?
Right.
And maybe ultimately it might make sense for the coupler to also negotiate ocean-ocean coupling, right? I think what we want at first is the flexibility to be able to run a regional model standalone as we're doing now, or within the coupled system, and extracting ocean boundary conditions either from a file, from reanalysis, or from a larger scale model, right? So for example, in the Atlantic, I think that it would make sense to use something like what Alan and Eric are running at FSU, where you have a North Atlantic model at a reasonably high resolution that's maybe assimilative, and then extract boundary conditions maybe on the fly from that, right? But you might also be able to do it by first running the so that there would be a synchronous way of concurrent way of running both a regional and let's say a larger scale model, whether it's a basin scale or a global scale. It's kind of immaterial. But you may also want to set it up in a configuration where you run your larger scale model first for whatever months, and then extract boundary conditions from that for your regional domain and run it that way. Still being able to remain coupled to either a dynamic or forced atmosphere. So there's a few degrees of freedom here, right? And they would each have some advantages and disadvantages, right? If you can run concurrently, you can help. So one of the things that we've learned with ROMs over the years is that the higher frequency that you can provide the boundary conditions, the better your solution looks very often, especially those California currents, right? So when we first started forcing with monthly boundary conditions, it was horrible. We went to weekly, was better, and then you do some experiments at even higher frequency. There was an improvement, and your domain may require that. Maybe there's some areas that you don't, and you're happy, right? So if you can run concurrently, you can go down to almost a delta T, right? To run them together, and that may be what's required depending on how accurate you need your solution to be.